Hey everyone, today I want to look at this sort of geometric inequality problem, and this came from a comment on a Mind Your Decisions video. It was like on a similar sort of geometric inequality question. And so the question says, triangle ABC is right angled at B. So let me quickly sketch that. Okay, so I'm going to call this A. B is where the right angle is, and then this will be C. A semicircle whose center lies on BC touches the lines A, B, and C. So by touches, I'm assuming it just means tangent. If the radius of the circle is 10 centimeters, or just 10 units, find the minimum area of a triangle ABC. So the idea is that we have a right triangle with some semicircle placed on one of the legs of the triangle, and then that semicircle is um, tangent to this right triangle at the other sides. So notice that one fact about circles and tangents is that if you have a tangent to a circle, let's say it's tangent at this point, then if you connect the tangency point to the center of the circle, then you make a right angle. So since the center lies on BC, and and we know that wherever the tangency point is on AB, it has to be such that it makes a right angle if I draw. So like, for instance, if it were here and I draw, well, I notice this isn't a right angle. The only point where you get a right angle from this point to AB is exactly at B. So we know that this uh, circle is tangent to AB at the point B. Okay, so this distance BO is 10. And so now we can just draw the rest of our semicircle. I'm going to sort of struggle to draw this, but let's assume it kind of looks like that. So then here we have 10, and then I'll call this point the tangency point D here. So if I draw this line from O to D, I know that's going to make a right angle here. Okay, so now let's make some geometric observations. Um, so the first thing I'm going to do is sort of just put in some dummy variables, and that way we can get, an expression um, for the area of ABC in terms of some variables, and then we're going to minimize that function. And, hopefully we can get it down to just one variable, and then we can apply calculus. Um, so the first thing to do is, um, well, there's kind of two ways to look at it. So one, looking from, let's look from A first, because A comes first. Okay. So A here, um, the line segments AB and AD are both tangent to this circle. And it's a well-known theorem that these line segments, these lengths are going to be congruent. So I'm gonna put Z just because this is how I labeled it when I was working the problem. Um, so these two lengths are Z, okay? And again, they're equal by a theorem about tangents. And you can kind of see it that um, uh, how is it again? I forget. Um, but but that's besides the point, okay? It's just a well-known geometry theorem. I'm kind of rusty on geometry proofs, but I remember the facts, okay? So now let's call this remaining side length of the hypotenuse x, and let's call this one y, okay? This remaining side length, y. Uh, so, so we have z and z here, and then we have x and y. Now, there are two ways to sort of go about this. Okay, so this length is 10. So you can use the Pythagorean theorem on the triangle ODC, or you can use the so-called power of a point theorem, which states that the distance, um, essentially the distance of like a tangent line squared is equal to the distance that hits a circle times the distance that hits the circle at the other end. So in this case, that would be y times y plus 20. Uh, and if you do the Pythagorean theorem, you're going to get essentially the same thing because you'll have a 10 squared and a 10 squared that cancel out. So first observation is that x squared equals y times y plus 20. Okay, that's our first observation. Now, the second observation is we can use the Pythagorean theorem on this whole triangle. And so notice like here we have z squared, and this side length is going to be, z plus x. And this one is going to be y plus 20. Okay, so notice what happens is that you're gonna have a z squared here and a z squared here that cancel out, and then you're gonna have an x squared here, which we can replace by y plus 20. And so what happens is you get, from the hypotenuse, you get 2zx plus y times y plus 20 is equal to y plus 20 squared. And so therefore we can subtract y times y plus 20 on both sides, and that leaves us with zx is equal to 10 times y plus 20. Okay. Now this relationship can also be brought about by noticing that the right triangle ODC is actually similar to the triangle ABC, because you have a right angle here and a right angle here, and then they share the same common angle. So this relationship can actually be obtained from similar triangle ratio. Okay, so now let's see. Hold on, just a sec. Okay, so what we do here now is let's look at the area of the triangle, right? So the area of the triangle is, of course, 1/2 base times height, so 1/2 z times y plus 20. Okay. So we want this to be in terms of one variable. Now notice that here, this x term we can express in terms of y. Okay, so let's look at this equation, and we can write this as z times the square root of y times y plus 20. And this is equal to 10 times y plus 20. And so therefore we can solve for z in terms of y, right? We divide this, and this will give us 10 times the square root of y plus 20 over the square root of y. Okay? And this means that we can plug this expression in to our area, right? Because we have z times y plus 20, so we can plug in what z is, and then we just have a as a function of y is equal to 1/2 times 10 times, now we have square root of y plus 20 times y plus 20, so I'm just going to call that y plus 20 to the 3/2, and then divided by the square root of y. Okay, so of course this 1/2 times 10 is just 5. So now we have our area in terms of one variable, and so we can differentiate and solve for 0. So a prime of y, I'm going to ignore the 5 because the 5 doesn't matter when we're solving for, so I'm just going to divide by 5 here. Okay, so we have, 3 halves times y plus 20, well, I guess just square root of y plus 20 over square root of y, minus, so we're going to have minus 1 halves, and then I guess this will be square root of y plus 20 over square root of y all cubed. So here I've just done the product rule instead of the quotient rule because it makes it easier to solve for 0, because now we have something minus something, right? Now, notice that this quantity y plus 20 over, or sorry, square root of y plus 20 over square root of y can never be 0, right? Because for this to be 0, you would have to imagine y plus 20 being 0, which means y is negative 20, but then, this wouldn't be defined, and of course, y isn't negative because it's a length. So that means that if I replace this expression by a dummy variable, okay, then what we have really is that if we multiply by 2 on both sides, we have 3u equals u cubed. And since u can't be equal to 0, this means that u squared is equal to 3. And u is also positive, right? Because these square roots are, taken to be positive square roots. So this means that u, which is equal to y plus 20, well, this actually gives us u squared is just y plus 20 over y, which is 1 plus 20 over y, meaning that if we subtract 1 on both sides, we get 20 over y equals 2, and therefore y is equal to 10. And now that we have y is equal to 10, we can plug that into our expression. So now I guess it should be checked that that this is in fact a minimum, right? So the way you would check that is by taking another derivative and checking that the second derivative of a at y equals 10 is positive. Now, I'm not going to do this. You can kind of argue that as y gets close to, like, smaller, right? So notice that this was the only, real solution to a prime of y equals 0, okay? Now, as y decreases, okay, this denominator is getting closer to 0, so the area is going to blow up, right? On the other hand, if y is getting larger, then since this will increase approximately at the rate of y, or 5y, as y gets large. And so if this is growing at the same rate as y, then as y goes to infinity, a of y is also going to go to infinity. So we see at both extreme ends, as y goes to 0 and as y goes to infinity, the area is getting bigger, and therefore this is a minimum, right? It wouldn't be a maximum because this is a continuous function on the interval 0 to infinity, right? So if it's going to infinity here, and it's going to infinity here, and we know that we have some critical point, right? Then that means that it has to be a point where the slope actually changes from negative to positive, and therefore this is a minimum. Okay? So so now we plug in a of 10. So this is 5 times 30 to the 3 halves over square root of 10. Okay, so this is going to be 150 times the square root of 30 over 10, and that's just 150 square root of 3. Okay? So this is the minimum area. Now, another thing that's kind of interesting is that if you look at the other side, like if you look at z, okay, so we have y is equal to 10, okay? So that means this side length is equal to 30. Now z, what was z? Okay, z was 10 times square root of y plus 20 over square root of y. If we plug in y equals 10, you get 10 times the square root of 30 over the square root of 10, which means this is 10 root 3. So what does that mean? That means that this is a right triangle such that the smaller leg, or sorry, the bigger leg is square root of 3 times the smaller leg. So this is a 30, 60, 90 triangle, which I thought was really cool. That the minimum area triangle happens to be such a special triangle. So yeah, that's it for this video, and I promise at some point I'll upload more, but I've just been kind of lazy. So yeah, I hope you enjoyed this video, and I'll see you next time.